All right, today we begin chapter 6. All of our theorems here will be ultimately inequalities, which will say that in certain conditions we'll have a greater angle or a greater side. And here in section 6.1, we begin with a theorem called the Anisosceles triangle theorem. And just to sort of set the stage here, this does build upon or extend, if you like, the isosceles triangle theorem and also the converse of the isosceles triangle theorem. The ITT says, of course, that if you have a pair of equal sides in a triangle, the angles opposite are equal. And the converse says that if you have a pair of equal angles in a triangle, the sides opposite are equal. And of course, then it follows from this that if you have a pair of unequal sides in a triangle, the angles opposite are unequal, because if the angles opposite were equal, the sides would have had to have been equal. And conversely, if you have a pair of unequal angles in a triangle, the sides opposite are unequal, because if the sides were equal, the angles would have been equal. But then let us ask another question. Okay, so let us say that in a triangle we have a pair of unequal sides, follows that the angles opposite are unequal. Can we know which is the greater of the opposite angles based upon the comparison of the lengths of the sides? And the answer to that is absolutely yes. And conversely, we might ask, if we have a pair of unequal angles in a triangle, can we say which of the opposite sides is greater? They cannot be equal. And the answer is absolutely yes. And that's the subject matter for today. Just a quick review and the introduction of a new postulate. And the new postulate will be just strictly algebraic in nature. In this section, we have no new geometrical postulates. From a geometrical point of view, this chapter is just applications of what we've seen before, but we'll need one new anyway. Algebraic postulate. So first of all, a review of the triangle exterior angle inequality. As for geometrical results upon which this chapter builds, this is one of the ones that is fundamental for us. And the triangle exterior angle inequality says that each exterior angle of a triangle is greater than either of its remotes. So in the diagram in front of you, angle 1 is exterior, its remotes are 2 and 3. So then by the TEAI, 1 is greater than 2, and 1 is also greater than 3. Also, let us postulate that the greater than relation is transitive. That is, if A is greater than B and B is greater than C, then A must be greater than C. I think you'll find this just as obviously true as the transitivity of equality. And perhaps I should add as well that immediately then we have the transitivity of the less than relation, because to say that B is less than A is simply to say that A is greater than B. Once you've defined what greater than is, or once you've introduced the notion of greater than, less than is just if you turn it around. Okay, so we have transitivity of greater than and transitivity also of less than. And let me remind you as well of a result that we proved in a previous chapter, chapter 4, I think, one of the first proofs that we did when we proved a set of results, basic results about part-whole relationships. And it's that the whole is greater than the part. So if you have some whole, either for us a segment or an angle that's been divided into some number of parts, then the whole is always greater than any of the parts, which we call WGP, whole greater than part. All right, so here are the results for today. They're called the Anisosceles triangle theorem and the converse of the Anisosceles triangle theorem. These names, I'll take credit, are my own creation. I wanted good names for these. And anisosceles simply means not isosceles. So if we have a not isosceles triangle, that means that presumably we have a pair of unequal sides. And what the theorem says is that the angle that is opposite the greater of the two sides is the greater of the two opposite angles. Okay, so greater angle opposite greater side. And conversely, if you have a pair of unequal angles with one greater than the other, then the side opposite the greater angle is the greater of the opposite sides. So this is, I think, exactly what you would expect. All right, so let's talk about the proof of the Anisosceles triangle theorem. So we have triangle ABC with side AB greater than side BC. And we wish to prove that angle BCA, which is the side opposite AB, is greater than angle BAC, which is the angle opposite side BC. Now, the strategy is this, and the strategy is ultimately Euclid's. We've seen this strategy carried out before. What we know by the ruler postulate is that since AB is greater than BC, there exists a point D. I'll just use a circle for a point. There exists a point D on AB such that BD is equal to BC. That is, if we have a greater segment than one segment greater than another, then we can carve off from that greater segment a part equal to the smaller. This is just direct application of the ruler postulate. And then we connect that point D to C. And to mark the diagram up, we have chosen the point D so that BD is equal to BC. And of course, you'll notice immediately that we, of course, do have an isosceles triangle. So let me mark some angles for you. They'll be the crucial angles. So I'll call them angles 1 and 2 and 3. And notice that 3 is simply a rename for angle BAC. And then since we've numbered other angles, I'll also number angle BCA. And the diagram means to indicate that 4 refers to angle BCA. It's nice in this case to refer to angles by number. All right, so first of all, ask yourself, what do we know about angles 1 and 2? Clearly they're equal. Okay, that's just the isosceles triangle theorem. Now ask yourself what you know about the relationship of angle 2 to angle 3. Students often don't see the relationship here. What you need to notice is that 2 is an exterior angle for triangle ADC. Look at triangle ADC. 2 is exterior, 3 is one of its remotes, so it follows that 2 is greater than 3 by the triangle exterior angle inequality. But we knew that 1 was equal to 2, so it now follows that 1 is greater than 3. Now ask yourself about the relationship of 4 to 1. 1 is just part of 4. So by WGP, whole greater than part, it follows that 4 is greater than 1. But 1 was greater than 3, so by the transitivity of the greater than relation, it follows that 4 is greater than 3. That's the proof. It's a very nice little proof. Simple, I think. Very direct, but very nice proof. So it now follows finally that 4 is greater than 3, but 4 was a rename for BCA and 3 was a rename for BAC, so the conclusion has been proven. All right, now let's consider the converse of the ATT, which tells us that if we have in a triangle one angle greater than another, then the side opposite the greater of the two angles is the greater opposite side. So in this case, we're given that angle C is greater than angle A and wish to prove that AB is greater than BC. Notice that AB is the side opposite angle C and BC is the side opposite angle A. Okay, now we do this indirectly and build upon the ATT. Okay, and this is also just like utterly Euclidean. The proof of the ATT is just the Euclidean strategy. This is also the Euclidean strategy as well. Okay, so what do we assume? Oh, we have to be careful not to make a mistake here. Students will occasionally make the mistake that they'll say that the negation of, the denial of AB greater than BC is that AB is less than BC. That's not correct. The negation of a statement must be false when and only when that statement is true. And if you say that the negation of AB greater than BC is AB less than BC, that doesn't necessarily have to be like false if the original is true, because there's a possibility that's been overlooked. That is that AB is equal to BC. Okay, so let's be careful about this. So our original assumption should be that AB, and here's a nice symbol for you, AB is not greater than BC. And this means we have two possibilities. So we have two possibilities, and they have to be considered. And it has to be shown that each leads to a contradiction. So one is that AB is equal to BC, and the other is that AB is less than BC. We have to consider both of these possibilities and show that each leads to a contradiction. Okay, so the first one, that AB is equal to BC. Well, that one's easy, right? If AB is equal to BC, then the triangle is isosceles, which means that angle A is equal to angle C, but that contradicts the given. Okay, now think about AB less than BC. Well, keep in mind that the Anisosceles triangle theorem has been proven at this point in time, so of course then just a moment ago, but since it has been proven, it may be used. And if we use it, if we apply it to number 2, it follows, if AB is less than BC, that angle C is less than angle A. Okay, because angle C is this angle opposite side AB. But that contradicts the given as well. Okay, the given says that angle C is greater than angle A, not the other way around, that C is less than A. So both of these possibilities independently leads to a contradiction, and so we've closed off both of these possibilities, which means that our original assumption is false. It is false that AB is not greater than BC, which means, of course, that AB is greater than BC. And I perhaps I was a bit harsh here, but I did want to mention one final matter and then I'll be done. Students will sometimes misunderstand the Anisosceles triangle theorem in the same kind of way that they will sometimes misunderstand the isosceles triangle theorem. Sometimes people will misunderstand the isosceles triangle theorem to concern the relationship between pairs of triangles. Um, they might think that, say, if you have two triangles and two sides in one equal two sides in the other, then something about angles. That's just completely mistaken. The isosceles triangle theorem is about angle relationships in a single triangle, just one. Okay, it does not compare pairs of triangles together. It's not like congruence. The anisosceles and the converse of the anisosceles triangle theorem are like this as well. Okay, they're not about the comparisons of two triangles. They're just about a single triangle. Okay, so the anisosceles triangle theorem does not say that if you have two triangles and a side of one is greater than a side of the other, then the angle opposite in one is greater than the angle opposite in the other. It does not say that, and it's good that it does not say that because that is false. And I'm not going to hop over to GeoGebra, but I think it would be a good use of your time to construct a counterexample to the conjecture of GeoGebra. And the converse is false as well. That is, if you have two distinct triangles and an angle in one greater than an angle in the other, it just does not follow that the side opposite in one is greater than the side opposite in the other. So just keep this in mind. The anisosceles triangle theorem and its converse are just about a single triangle. They're not about comparisons of triangles.